In 1965, Richard Feynman proposed a double-slit experiment to investigate the wave properties of electrons. The experiment was later carried out using the arrangement shown. We have a beam of electrons directed at the barrier with two slits. So what's happening here is we have electrons, which are acting like waves, traveling towards these two slits. And then when they pass through the individual slits, they diffract. As those waves diffract, they spread out and they travel towards various points along this detector. The waves will interfere constructively and destructively, and you'll see maxima and minima along this detector. And that pattern is shown over here. So let's carry on reading the question. So the detector recorded the positions where electrons arrived after passing through the slits. The following pattern was obtained. Black dots represent points where the electrons were detected. A band where electrons were not detected has been labeled X. So that's what we see over here. Electrons are not detected there. And a band where electrons were detected has been labeled Y, which is this bit over here. So on this diffraction pattern, we see maxima, which are the regions where you see loads of electrons landing. These are the maxima, regions of max constructive interference. And then in between, you see minima, regions of max destructive interference. And then the rest of the question says that the path difference for electrons arriving at band X from the separate slits was 2.5 times 10 to the minus 11. And for electrons arriving at band Y, the path difference was 5 times 10 to the minus 11. Explain why this pattern is observed when the electron energy is 9.6 times 10 to the minus 17. The electrons are traveling at non-relativistic speeds. Okay, so maybe we'll write some of that stuff down on our diagram. So we have the path difference at band X from the two slits is 2.5 times 10 to the minus 11, and for Y it's 5 times 10 to the minus 11. So it might be a bit hard to write over here, it's going to get quite cramped, so I'll just put it on the right hand side. So at X, the path difference, which I'll just write as PD, is equal to 2.5 times 10 to the minus 11, and at Y, the path difference was 5 times 10 to the minus 11. So what actually is path difference? I'll just quickly go up to this diagram to explain that. So imagine if you have two rays of electrons traveling to a particular point on your detector. So let's say these two rays meet at this point over here. The path difference is the difference in distance traveled by these two rays. So the path difference will be the extra distance traveled by this wave at the bottom over here. And then you could imagine as you move this point up along the detector, the path difference will increase. This length will get longer than this one, the higher that meeting point is. So let's actually discuss what the path difference would be at different points along this screen, or along this detector. So at your regions of max constructive interference, so these regions over here, the path difference will be an integer multiple of wavelength. So for our central maximum, this is our 0th order maximum, the path difference would be 0 wavelengths. And then at our first order maximum, the path difference would be 1 wavelength. And that's the same thing over here. This is also our first order maximum. And then you have your second order maximum as well. Path difference is 2 wavelengths. Same thing over here. And then for our minima, so that's going to be these regions in between, the path difference will be an integer plus a half of a wavelength. So I'll start by writing out the orders. So these two minima over here are the first order minima. So this will be n is equal to 1, this will be n is equal to 1 as well. And the corresponding path differences would be half of a wavelength. So I'll just squeeze that in over here. And then for these two minima over here and here, they are our second order minima, n equals 2. The path difference will be 1.5 wavelengths. So then, from this diagram, and the fact that in the question we were told what the path differences are at x and y, which I've written over here, we can work out what the wavelength should be that has created this pattern. If we know that the path difference at x is equal to half of a wavelength, and we know the path difference at x is 2.5 times 10 to the minus 11, we can equate those two things and then work out what the wavelength is. We can do the same thing at the maximum y, so we know the path difference there is 1 wavelength, we can equate that to the path difference at y, which we're given in the question, which is 5 times 10 to the minus 11, and again work out what the wavelength would be. So let's write that down. So let's start with point x. Okay, so at point x, we have our first order minimum. That's over here. So we have max destructive interference. The path difference is half of a wavelength. The two waves that are meeting at that point will be in antiphase. So the path difference is half of a wavelength. That corresponds to the waves being in antiphase. And therefore we see max destructive interference. And now we can use the fact that the path difference is also 2.5 times 10 to the minus 11. So we can say that half of a wavelength, which again is the path difference at x, is equal to 2.5 times 10 to the minus 11 meters. And then we can rearrange that for lambda. So times this side by 2, so bring the 2 over to the right-hand side, we get lambda is equal to 5 times 10 to the minus 11 meters. So if the path differences at band x and band y are these two numbers, that means that the wavelength of electrons that has created this diffraction pattern over here must be 5 times 10 to the minus 11 meters. Let's just do the same thing for y as well. So at y, which was our first order maximum, we have max constructive interference. The path difference here is one wavelength. That corresponds to the two waves being in phase. So let's write that down. Path difference is one wavelength. That corresponds to the waves being in phase. And therefore you have max constructive interference, which is why we see a bright band over there. More electrons land at the spot. And again, the path difference at band y was 5 times 10 to the minus 11. Path difference is also one wavelength, as at y it's the first order maximum. So we equate that one wavelength to that 5 times 10 to the minus 11, and we get the exact same thing as before. So the wavelength, as we can obviously see from that equation there, must also be 5 times 10 to the minus 11 meters. So that agrees with the path difference at point x. For both x and y, we get a wavelength of 5 times 10 to the minus 11 meters. Okay, so that's half of the question done. The other half of this 6 marker is to discuss this sentence over here. Explain why this pattern is observed when the electron energy is this. So, if this diffraction pattern over here requires a wavelength of 5 times 10 to the minus 11 meters to exist, does this electron energy correspond to that? So that's the second half of this question. It's working out the de Broglie wavelength of this electron energy over here. De Broglie wavelength is h over p. So we need to work out the momentum of the electrons. We can do so by considering the kinetic energy. So the kinetic energy is this, 9.6 times 10 to the minus 17. I'm going to use this form of the kinetic energy equation, p squared over 2m. And the reason I'm using that form of the kinetic energy equation is because I can then bring these two equations together. I can link them together through p. So I can rearrange this equation for p and then sub it into this one. If you're not sure where this kinetic energy equation comes from, well, if you replace the p that we have over here with mv and then square it, so m squared v squared, that's still divided by 2m. A factor of m's cancels out, and then we're left with mv squared over 2, which is half mv squared. That is kinetic energy. Okay, so then we're going to rearrange that kinetic energy equation. Just going to rub this bit out over here. Let's rearrange this kinetic energy equation over here for p. So bring the 2m up here and then square root it. So we'll end up then with p is equal to the square root of 2me. And then, again, we're trying to work out the de Broglie wavelength of the electrons. We can substitute or replace this p with root 2me. lambda is then equal to h over root 2 e. And then what do we have from this? So we have the electron energy, the kinetic energy of the electrons, 9.6 times 10 to the minus 17. That is this value of E over here. Planck's constant and the mass of the electron, they're both constants. So let's just sub those in. So Planck's constant is 6.63 times 10 to the minus 34. And then we're dividing that by the square root of 2 times the mass of an electron, which is 9.11 times 10 to the minus 31, and then timesing that by the kinetic energy, which was 9.6 times 10 to the minus 17. And that ends up giving us 5.013 times 10 to the minus 11. And notice how this wavelength that we've worked out, the de Broglie wavelength that we worked out from the kinetic energy of the electrons, is pretty much equal to 5 times 10 to the minus 11 meters. That was the wavelength that we got from the path differences for x and y. So they're in agreement. If the path differences were what they were told to be in the question, that means the wavelength of the electrons needed to be 5 times 10 to the minus 11 meters to create this diffraction pattern. And the kinetic energy of the electrons that we had gave us a de Broglie wavelength of 5.0 times 10 to the minus 11 meters, so they agree. So therefore the de Broglie wavelength agrees with the wavelength that we got from the path differences. So agrees with lambda calculated from path differences.